All right. Oh, here we go. All right. Here we are. Yes, we're good. All right. So Monday. Wow. How excited are we? Yes, it's a new week. And I guess now we're starting to get with the swing of things. It certainly doesn't feel like the summer anymore, does it? No. So now the last time we were working in chapter 5B, we just started looking at some key properties for radicals. And we're going to carry on with that today. Of course, we'll also do a lot of other new things. And I have one or two fun videos for us to look at, which will be very helpful to understand what's going on here. So we did already look at multiplication and division. Now, I did mention, I think the last time, that addition and subtraction are just a little bit trickier. And the reason for that is because you can't actually combine radicals unless the same value is under the square root sign. So let's say this is our general example. So imagine that we have two constants, a and b, and then we have two radicals, just c. You notice they're both the same radical. If that's the case, then we can just add up the two coefficients, and we end up with a plus b all multiplied by radical c. The same thing holds for subtraction. But again, the key is that these have to be the same radicals. Otherwise, this is not going to work. Okay, so it's equivalent to having, let's say, 3x plus 4x equals 7x. If you had instead 3x plus 4y, you cannot do anything with them. And the same thing holds with radicals. Okay, that radical has to be the same, and if it is, then you can certainly add them or subtract them. That wasn't true, if you recall, with multiplication and division. We can multiply or divide any radicals that we like. Of course, in the case of division, we have to avoid division by 0. Other than that, we can do anything. Now, sometimes, though, you may not think you can combine these, but it may turn out that if you simplify your radical, it might turn out to be the case that you can, in fact, add them or subtract them. And that's another one of the reasons why we always like to simplify our radicals, because you may think that you can't add them together, and it may turn out that you can, because you didn't simplify the radicals. So again, we see that it always comes in handy if you've simplified your expressions as much as possible, because then it'll be more obvious what you can and cannot do with them. So let's look at a few quick examples. Now these, of course, we have the same radicals. So all I have to do is add these together to get 7 radical 2. All right, and for the same, based on the same logic, these are both the same. So now I have 5 minus 2 radical 3, or this reduces very nicely to 3 radical 3. But if I had something like this, there's nothing I can do with it, okay? Because they're different radicals and they cannot be simplified any further. So that's it, you're done. But imagine if you had something like this. Let me see if I can come up with a good one. How about 4 radical 3 plus 9 radical 300. Okay, let's try that one. Now, again, like I said before, it may not be clear. At first glance, it appears there's nothing you can do. You have 3 and 300, they're clearly not the same thing, but you might notice with the 300, oh, look at that. Okay, now look what's going to happen. And so that's going to be 4 radical 3 plus 9 times 10 times radical 3. So I've got 4 radical 3 plus 90 radical 3. And wow, what do you know? After all that, we were able to combine these. But that's because we simplified and we found that both of them have a common radical of 3. That wasn't true over here. There's nothing we can do. It's done. Okay, so whenever you have unusually large radicals, the first thing you should always do is see if there's some way you can simplify it, especially if you can break it down into 2 factors, one of which is a perfect square. That's the ideal scenario. It doesn't have to be a perfect square, but often you can reduce these somewhat. And if you do find a common radical, then you can feel free to add them or subtract them. Okay, so that's not too bad. Now, rationalizing denominators. This is an interesting idea. In math, as a rule of thumb, we know that we try to simplify everything to the extent that's possible, but there's other rules that we typically follow. Like, for example, imagine if you had a quadratic equation like this. 3x squared plus 4x plus 7. By convention, what we always try to do here is have the highest exponents of x first, and we work our way down to the lower exponents and then finally the constant. So if you actually started out with something like this, this is not wrong. And these are the same thing, but by convention, you would turn around and rewrite it as 3x squared plus 4x plus 7. So here we're about to encounter something very similar. One of the rules of thumb with mathematical expressions is that we try to avoid having radicals in the denominator. Okay. And again, it's not that what we have is incorrect if we have a radical in the denominator, but if we get it out of there, it's often easier to see what kind of operations we can perform in them. So it's not just like because it looks nicer, but because it can often help us notice simplifications, other simplifications that we can use. Now, what we're going to do is this. Just a quick reminder. You're all aware, and we'll just quickly review this, that remember way back when you tried to combine fractions. Let's say you had something like this going on. Now, would you leave it like that? No. The technique that you would want to follow is to find a common denominator for each of these two terms. How do I do that? What I'm going to do is multiply 2 by 4/4. Now, why am I doing that? Well, first of all, it will get me a common denominator. And secondly, am I allowed to do this? Yes, because 4/4 is just 1. I can multiply any number by 1 without affecting its value. So what that will leave me with is 3/4 plus 8/4. And that's going to leave me with 11/4. All right, so remember that when we're doing these rationalizing. And by the way, if you notice, it says rationalizing. The reason why the word is there is because, remember, a rational number, last week we mentioned that as far as square roots are concerned, the square root of a perfect square is always rational. The square root of any other number is irrational. So when we say the words rationalizing the denominators, what we're basically doing is getting rid of irrational numbers in the denominator. Okay, and that of course represents most square roots. Okay, now let's take a look at some of these. Now, I want to point out that in some of these cases, what we're doing here is not going to simplify anything, but again, by convention, something like this, we can easily get rid of this irrational number in the denominator or multiplying it by a special version of 1. This, of course, is 1. But why did I choose radical 3 over radical 3? Because that's what's in the denominator here. And as you see, what happens is that in the numerator, I end up with radical 3. The denominator, I end up with 3. And this is the final result. Now, these two numbers certainly do equal each other. But again, by convention, we always want to use this one. This is the preferred form. You might remember from trigonometry in high school, you would often end up with answers like 1 over radical 2. And so what would you do to get rid of that radical? Okay, this is going to end up being radical 2 over 2. If you look at a chart of cosines and sines, et cetera, you won't ever see 1 over radical 2 listed there. It'll be converted into radical 2 over 2. Now, in this case, though, you see what we got. I think you'll all agree that this is scary and this is pretty straightforward. In other words, this time, rationalizing the denominator, actually simplified our final result. And so everybody, I think, will agree that 12 radical 2 is much nicer and simpler than 24 over radical 2. So this time we got a double bonus. We not only got rid of the irrational number in the denominator, we have an expression now which is a little bit simpler. Okay, so it's not a difficult thing to do, but it's good practice. And again, like I said, sometimes it'll lead us to even simpler results, which is always our objective. We like simplicity in math. Okay, now, here's another situation you might occasionally run into. What if we have the ratios of perfect squares? Like, for example, something like this. Now, we've already seen this. You can go back and forth. Both of these mean the same thing. But sometimes it helps to rewrite our expression as one or the other. Okay, so this is a good starting point. If you think you can simplify your expression, you might want to go from this to this or this to this. So let me show you some quick examples. Like here, radical 25 over 9. Look at that. By splitting it up into two radicals, I end up with 5/3. So I think you'll agree that this is far preferable to this. Okay, that's 5/3. Yeah, that's pretty straightforward. Radical 25 over 9. That's a little bit tricky. And then you can see another one here, radical 36 over radical 49. I break it up into two pieces, and I have 6/7 as my solution. So in others, I think you'll all agree.
But I need my mood stabilizers.
6/7 is a lot simpler than radical 36 over 49. Now, it doesn't always, I mean, you're not always going to be able to find these nice results, but you should look for them anytime you have radicals involved. All right, now, here's an interesting application of all of this. You might say, well, you know, radicals, where do you ever see radicals in the real world? Well, here's a very fun example. This is something, by the way, just for the fun of it, I'm going to ask you about a very famous novel. Okay, what we're about to look at shows up prominently in a very famous novel. I'm going to give you some hints and see if you've ever heard of this novel. It probably came out, I'm going to say 2004, 2003. So you were kind of young at the time, but it was made into a very famous movie. So this book involved, well, a lot of numbers. I'll give you another. Well, I'll start with the star. The movie starred Tom Hanks, and it involved numbers, and it also involved the painter of the Mona Lisa. So, what book am I referring to here? What book? Ooh, okay. Oh, here we go. Somebody has it. The Da Vinci Code. Oh, yes. Now, the Da Vinci Code at the time, and you know, this is like almost 20 years ago now, it was certainly one of the most popular books and movies for many, many years. I mean, it was something everybody was constantly talking about because what the author Dan Brown is able to do is take art and history and architecture and especially math and tie them together into a very interesting plot, which could in principle be true, although it probably isn't. But it's one of those things where it's just fun and you learn a lot too. So if you find yourself with an unusually tedious weekend, what you might want to think about doing is grab this movie and watch it if you haven't already seen it, because it's good and you'll learn something. All right, but the same author did write a few others, same characters, which were also very good. But this one particular concept showed up over and over again in the movie and in the book. It's what I'm about to show you, and it's called the golden ratio. Okay, now this is something that Da Vinci mentioned in his writings, and he was aware of it. This idea was thought of in maybe the 14th, 15th century mathematicians had started to study this very interesting idea. Now, first things first, this is the Greek letter phi. It's spelled phi, but it's pronounced phi. This is only approximately correct. It actually goes out forever without repeating. So in other words, this phi is irrational. How do you know? Because it's not, although I've got the approximate signs here, it does go out forever and it does not repeat. So therefore, this is neither terminating nor repeating. So phi is an irrational number and it is a function of radical 5. And it has a lot of interesting properties. You look at this and say, wow, who cares? What is this number all about? Why does it matter? Well, because now, you know, some of this may or may not be true, but it has supposedly been used a great deal in art and architecture throughout the centuries, as well as it does sometimes show up in nature. It also has applications to human anatomy. It shows up in a lot of surprising places. So where does it come from? Now, here's something that you might remember from high school. The Fibonacci sequence. Oh my God. What is that? Is that bringing back fun memories? Yes. So what exactly are we looking at here? We have all these numbers and they do go on forever. But what pattern do you see here? Well, after the first two, each number after that is simply the sum of the previous two values. Okay, so 1 and 1 is 2. 1 and 2 is 3. 3 and 2 is 5. 5 and 3 is 8. As you can see, it goes on and on forever. By the way, Fibonacci popped up in our video about the history of zero. If you might recall, he was one of the people who wrote in his works how important zero is. So Fibonacci was a very important mathematician in during the Renaissance. Fibonacci, I don't remember his exact name. Fibonacci is what he was called. I think his name was actually Leonardo or something like that. Let's check this out. All right, hold on.
Early bird club.
I know, I want to be an early bird.
All right. So here he is. Fibonacci was just his name. He used that for, I mean, he nobody called, he used that as when he wrote books, he would call himself Fibonacci, but his actual name was Leonardo. There it is, Leonardo of Pisa, or Leonardo Pisano. And he was considered to be the most talented mathematician of the Middle Ages. And so he was very well known. And a lot of what we have now is taken directly from his writings, including this golden ratio. In fact, there's a lot of other interesting things that can be done with it. Now, what does this have to do with the golden ratio? Well, you might not think there's any connection here, but what happens here is that if you take all the terms and calculate the ratios of every two consecutive terms, for example, 2 divided by 1, 3 divided by 2, 5 divided by 3, 8 divided by 5, all the way out. Look what happens to those numbers. They're getting closer and closer to the golden ratio, which, if you recall, is approximately 1.61803. So the golden ratio is actually derived from the Fibonacci sequence. Now, what is it for? Now, in terms of geometry, you can take these numbers, these Fibonacci numbers, and arrange them as a series of rectangles whose area is that number. In other words, 1, 1, 2, 3, 5, 8, 13, 21, and 34. And if you connect all these points in a very special way, you end up with the so-called golden spiral. That's the part that we're going to see showing up in art and architecture, the golden spiral. Okay, now I've got some interesting examples of it here. Like a seashell. Doesn't that seashell look like it follows the golden spiral? Yes, it does. You've all played with seashells when you were little kids, unless you live in Nebraska and you never saw the ocean. Yes, seashells, they're fun, they're cool, they're laying around all over the place just for the taking. And you grab one and you look at it, wow, how cool is that? So, yes. How about these flowers? Oh, this one on the left is a shell, but these other two are flowers. Does it look like the golden ratio is hiding in there? It sure does. Well, where else might we run into this? Human anatomy. Look at that. Doesn't your ear remind you of that golden spiral? Sure it does. And oh, by the way, in Da Vinci's writings, he mentioned that there's several ways in which the golden ratio shows up in the human body. For example, apparently the ratio of your height to the length of your legs equals 1.61803. It's the same as the golden ratio. Now look at these stairs. You think somebody had this golden spiral in mind when they designed these stairs? Now, we don't know that for sure, but I mean, it looks kind of interesting. Now, let's look at our hero, Mona Lisa. Everybody knows the Mona Lisa. Look at that curve that you can form. Now, a lot of people are very skeptical that Da Vinci actually painted this way on purpose, that he was following it, but he would have been aware of it at least. Okay, in other words, when he was a master of proportion, and proportion can often be expressed in terms of the golden ratio. So some people say yes, some say no, it was intentional, it wasn't intentional, it's hard to say. But our friend Lisa, well, there she is, giving you that look. And then the Last Supper. Now, these are not spirals, but these are the golden ratios. Apparently, they're all over the place in here. Yep, the old Last Supper. It's so sad because, he used a special kind of paint to do this on a wall somewhere in Florence, and it's let's just say it's falling apart. And so they're very worried about the condition of the Golden Supper. The Last Supper. But anyway, this is one of his most famous drawings, Vitruvius Man, where he's trying to show you how the ratio of his legs and his arms and his height all follow the golden ratio. And then finally, let's bring the 21st century into this. Here is a graph that was designed with the golden ratio in mind. Oh, now how cool is that? Wow, that is cool. But you can see that is clearly the golden spiral. But this was designed by a computer. All right. It clearly is not natural. It's not part of nature, but computer graphic designers could create something like this very quickly and easily. So if this is your area, you might have fun creating all these wonderful geometric shapes in Photoshop or Illustrator. Is anyone here studying graphic arts or graphic design? I usually have one or two in every class. No? Okay, but even if not, maybe you dabble in this stuff. Maybe you are like you're studying dance, but you like art too. Well, you might have some fun with this. It's complicated stuff, but it can be done. Okay, usually a lot of times these are done by mathematicians, and so because this is what they do, and the graphs are just part of it. But you can see it's very artistic too. And I bet if you hung this up in a gallery in the village, you could sell it for some nice money. Math art, who knew? All right. Now, before we get on to 5C, that was the end of chapter 5B. Here's 5C. And there's a lot of more fun stuff coming, but it just so happens that today we have some more cool videos. Let's see. Oh God, I had them right here. It's amazing how even if you only have a few things open, stuff just disappears. I mean, so where did it go? I guess I'll have to open it up. Oh, here it is. Jeez. Okay. All right. So there's two I'll tell you what, why don't we do this? I'm going to change the order that I had in mind today. I want you to see the golden ratio video because it's really interesting. I'm going to do that first and then we'll look at the other two. Okay. So let's jump ahead here and look at the golden ratio video. It's very well produced. It's a lot of fun, but it can be a little, it goes kind of fast. So you're not going to pick up on everything, but what you're going to discover is just how incredibly important and complicated this thing really is and how useful potentially. I think you'll find it very interesting. So we'll start with this one. And as usual, I'll send you the link. All right. And then you'll watch it at home. And then I think you'll be impressed. Okay. All right, let's check this out. Well, that was pretty impressive, wasn't it? It's a very complex idea, this golden ratio, and it's been studied by mathematicians for centuries. But you can see it does have a lot of interesting applications. And so the book, The Da Vinci Code, which I was discussing with you earlier, the plot heavily depends on this golden ratio. Now, you might find that surprising. Imagine a best-selling book involving math. It's not just math, though. By the way, the lead character who solves the mystery at the end, he in the book he's referred to as a professor of, I think, symbology or something like that at Harvard, because along the way Dan Brown throws in a lot of other very interesting and important ideas. And this, I don't think there is such a field of symbology, but it really it's quite an experience. And some of it you're not going to get in the movie. If you want more of the details, no, none of this is going to be in a quiz. This is just for the fun of it. Okay. Sometimes, the history of math is very interesting, and it's something that's worth noting. Not only where did it come from, but what can it be used for? And this is an example of that. Yeah, I'm not going to ask you on a test like who invented or who wrote the Da Vinci Code or something like that. But I think you'd find that, yes, math shows up in surprising places is what I'm getting at here. It really is everywhere. Okay, so, and sometimes in very interesting and fun ways. So remember, the Da Vinci Code, like I said, if you don't feel like reading a long novel, you can easily get the movie since it's about 20 years old now. It should be on Netflix or somewhere cheap or free. And you might want to check it out sooner rather than later, especially while you're in a math class and you're really in the mood to learn more about math. It's just very well done. It really is. It's fun. Even if you didn't know the first thing about math, you would still have fun with it. All right, now what we're going to do next is we're going to look, this one, although the title is Why Are There So Many Numbers? This is an excellent discussion that ties together the many different kinds of numbers that we've been analyzing. And he also provides a very interesting discussion about what imaginary numbers are really all about. So I think you'll like this. And he's a very interesting speaker too. So I think you'll get a lot out of this. So let me post this link. Yes, so hold on. Oh, wait, I'm sending it to the wrong place. There you go. All right, so let's check this out. All right, so that was a very good way of tying everything together, but I think he had an interesting way of explaining what imaginary numbers are, to think of it as a number in a completely different dimension. Because of course it's not on the real number line, so where is it? It was kind of an interesting idea, I thought. And he also reminded us of a lot of the concepts that we were learning earlier. Real numbers, imaginary, but also rational, irrational, and all the rest. He tied them together very nicely, I thought. And of course, it's always fun when you can see all this stuff visually. And also, there were some interesting ideas there about how and why these different numbers were invented. For example, the idea of negative numbers, according to the video at least, was brought about in part due to the need to explain the value of debt. Okay, if you owed somebody money, that could be expressed as a negative number. Now, before banking came along, this kind of thing wasn't very useful, but eventually it became necessary to have negative numbers, just like the zeros, which for the longest time was resisted, especially in Western math. And fractions too. I mean, who would think of such a thing? But eventually they were developed because there was an obvious need for them. So you can see everything we do in math at some point in history was somehow related to some real situation that needed an explanation. And so math was developed to come up with that explanation. All right, well, anyway, so now that we can get back to 5C, but before we do that, I just want to point out, there are some problem sets here on Moodle. There's 3 of them, one for each section. One is really meant for 5A, one for 5B, and one for 5C. So because we're now done with 5B, I don't want to wait too long to get started on these. What we do with these, whether we're online or not, what we've been doing in the past several years is using these as an attempt or as a way to practice for the first exam. So in other words, what you will be doing, I hope, is downloading this and writing out your answers, which we will go over, not, let's say not on Thursday, but next Monday. And that way, we just want to make sure that you're keeping up with the material, that you really understand everything. This is the best way to find that out. If you can do these problems, you're good. Because the test, the first midterm, will be very much like this. Now, we'll do the same thing then for the second problem set, and then finally we'll wrap that up with the third problem set. Okay, so for next Monday, I would like you to work on this. I'm not going to collect it. I'm not going to grade it. It is 100% just for your benefit to get some practice and make sure you're really following along. Right? And if you get stuck, you know, we can go over it in class. And if you're super stuck and you really don't get it, we can have a Zoom conference and we'll go over it. All right, so there it is. Don't forget. I'll remind you again on Thursday. In the meantime, we're ready to start 5C. All right, let's see. I had it open here a minute ago. What happened to it? There it is, 5C. The real numbers. Now, I think we already mentioned that all the real numbers are either rational or irrational. So we can express this more formally in terms of sets. Now, often in math, we use this very cool symbol, the fancy R, to represent the real numbers. So if I write that down, you know I'm talking about the real numbers. Now, as they mentioned in the video, like here's your real number line. And numbers like 0 and 1 and -1, they're easy to locate because they're rational numbers. The irrational numbers are hiding in there somewhere. We can't really find the exact location, but we know that they're in there. And we can prove it with geometry, as they showed you in the video. But what we do know is that there's an infinite number of numbers on this real number line, and every single one of them is either rational or irrational. So we're going to write this as the set of rational numbers. And then we're going to use the symbol U, which stands for union. And then we'll have the set of irrational numbers. The union means we're combining the two sets. These are both sets, okay? You can tell because of these braces. These are traditionally used in math to represent sets, and a set is simply a collection of objects. A set can be finite and it can be infinite, as these two are. So if you combine the rational and irrational numbers in one gigantic set, you'll end up with the real numbers. Now, by the way, I also want to point out that there are no numbers that can be both rational and irrational. So in set notation, what you could write is that, let me do this on the next slide. Whoops, no, that's not what I wanted. So in addition to this statement, which again simply indicates that all the real numbers must be either rational or irrational, we know one more thing. They do not overlap. There's no number which is both. So therefore, we can use the following notation. Okay, that upside down U, you might recall from high school, is intersection. And it means we're creating a set of all the values that are common to both sets, but that there is no such thing here. So we say that that equals the so-called empty set. No elements belong to this set because no number can be both rational and irrational. All right, so this is just a very formal way of expressing what we already know. All the real numbers are either rational or irrational, and no number can be both. Okay, so in English, that's all that it means. But we often in math like to write things in a more formal way because this way they're consistent and we can express a lot of other ideas with the same terminology. All right, now we're going to revisit some of the key properties of the real numbers. Some of these you've seen before and some of these you may have not. The ones you have seen, it may have been a while, so this will be good review. We're going to represent or identify 6 properties here of the real numbers. Okay, closure, which you may not have seen before, the commutative property, which I know you've seen before, the associative property, which again, I know you've seen it. You may have forgotten what it means, but you've definitely seen this. When you see it again, you'll say, oh, how did I forget that? Well, you know, it's been a while. If you haven't been thinking about math all this time, then you're going to start forgetting it, of course. And then the last 3, the first 2 you may not have seen before, the identity property and the inverse property. The last one, the distributive property, for sure you've seen that one. The question is, what do they mean? Okay, now some of these are very self-explanatory and some of these are a little bit more involved, but we need all of these to hold in order to derive any meaningful results with numbers. Okay, in other words, these properties ensure that all the operations that we perform in numbers are consistent. Okay, for example, the closure property, this one is pretty self-explanatory. If I add any 2 real numbers, no matter what they are, their sum will also be a real number. Okay, in other words, I can't create an imaginary number simply by adding 2 real numbers together. That's it. Yes, that's it. Now, by the way, this holds for multiplication as well. Now, by the way, we don't need to separately define this on subtraction because when you think about it, subtraction is really just the addition of 2 numbers, one of which is negative. So we're just going to define this for addition, and then we're going to do the same thing for multiplication. So, I mean, you can imagine where this is going. If I multiply two real numbers, A and B, no matter what they are, the result is also real. It cannot be imaginary. Okay, remember, imaginary means square root of -1 or some square root of some negative number. All right, now the next one, which you are well familiar with, the commutative property. The commutative property here is defined with respect to addition and multiplication. And basically what it tells us is that the order in which we add two numbers is irrelevant. All right, in other words, A plus B and B plus A mean the same thing. That's all it means in a nutshell. The order in which I add numbers does not make any difference to the value or result. Is it coming back in a big flash? Yes, it is. You're thinking, oh, I remember doing this in the 8th grade with good old Mrs. Smith. Yes, I remember her very well. All right, so here's some quick examples. And by the way, this applies to both positive and negative numbers. So like obviously 3 plus 4 and 4 plus 3 are the same. -2 plus 7, 7 plus -2. So you can see clearly the order in which I add numbers is not relevant. I can say the same thing for multiplication. Okay. So I'll give you a second to catch up, but what's coming next is multiplication. A times B equals B times A. It doesn't make any difference what order I multiply them in. Okay, it's the same thing. Now, you know these by heart. I mean, you intuitively understand this, but you may have forgotten that this is called the commutative property. Let me show you some examples. 3 times 4 is 12. 4 times 3 is 12. -2 times 7 is -14, as is 7 times -2. Now, this raises an interesting question, though. Is it true that the commutative property applies to subtraction or division or both? Well, let's think about that. Is the commutative property true for subtraction and or division? Well, let's find out. Let's say, is it true that 3 minus 4 equals 4 minus 3? No. Obviously, you see what I mean? It doesn't work here. How about this one? Is 2 divided by 3 equal to 3 divided by 2? No. By the way, this equal sign with a question mark means exactly what it says. Are they equal to each other? And the answer is no in both cases. So the commutative property only applies to addition and multiplication. With division and subtraction, the order of the operations does matter. And again, this is something you knew intuitively. You just might have forgotten that it's called the commutative property. All right. How about our old friend, the associative property? What was that one? Well, again, it's possible that you've forgotten it, but you definitely learned this at one point in time. Essentially, what it's saying is that when it comes to addition, if you apply parentheses to addition, it will not affect your results. Okay, in other words, you've got A plus B in parentheses plus C equals A plus in parentheses B plus C. placement of these parentheses does not affect the results. All right. Now, of course, it does affect the results for other operations, but not here. For just all addition, it doesn't matter. In fact, we don't even really need these parentheses. So, for example, here we go. 1 plus 2 plus 3. I've done it in two separate ways with two different groupings with my parentheses. And you can see in both cases, I just get 6. Same thing for the second row, or second example, 3 plus 6 plus 7. Any way you look at it, no matter where the parentheses are, you're going to wind up with 16. Okay, so the associative property applies to addition. Now, does it apply to multiplication? Well, when you stop and think about it, let's say if I put parentheses about any two numbers in a multiplication, does it affect the results? It does not. Okay, so let me show you some examples of that. And yeah, you can see right there, I've got here parentheses around A times B times C. And here on the right, I have A times parentheses B times C. These give me the same result. All right, so in a second, I'll show you an example of this. All right, so like here, for example, now, if you notice 2 times 3, I'm evaluating these first because they are parentheses and they do take precedence over multiplication. So that leaves me with 6 times 4, which is of course 24. In the second case, the parentheses around the 3 times 4, which means I have 2 times 12, which still gives me 24. Now that's still true with negative numbers. So down here in the first row, I have in parentheses -1 times 4 times 5, or -4 times 5, or -20. Below that, I have the parentheses around 4 and 5 instead of -1 and 4. So I've got -1 times 20, which of course is also -20. So that means that the associative property is defined for multiplication and addition. Now, it may not be the case. Let's see what we can do with subtraction and division. Suppose I have this. I'll start with -1 plus 2 plus 3. I'll rewrite this as 1 minus 2 plus 3. And now I'll write it like this. You see, we're in trouble, aren't we? Because we have 1 minus 5. If you evaluate what's in the parentheses, okay, so we're in trouble here. These do not equal each other. So in other words, yes, we can rewrite this, but the way we put the parentheses actually does affect the results. So associative property obviously does not hold for subtraction. And how about multiplication? I'm sorry, division. We know it works for multiplication. What about division? Suppose, for example, we have 1 divided by 2 divided by 3. that's 3/2. But if I have one, well, actually, this one is working. Is 1/2/3. So that worked. Now that doesn't guarantee it always works. I just happen to pick that example. Let's try this. Let's use the traditional symbols. Suppose I had this. 1 divided by 2. Well, that's actually what I just did. And so I could rewrite this as 1 divided by 2 divided by 3, which is 1/2/3, which is the same as 1/2 times 3/1. And then 1 divided by 2 divided by 3. Okay, it seems to be working. Where it's not going to work is if you start mixing and matching, if you've got other operations mixed in there, like multiplication or subtraction or whatever. But here it appears that this does seem to be working well for division. Okay, now here's an interesting property. This is the first one of the first ones you might not recognize. Possibly you have seen it, but maybe not with this name. We have the so-called identity property. There's two different ways we can have identities. Everybody knows that for any real number, if I add 0 to it, I'll still have a. Of course, adding 0 to a number doesn't change its value. So therefore, we refer to 0 as the identity element for addition. And by the way, that would also be true of subtraction. Remember, subtraction is just this anyway. Oh, sorry, I wrote the wrong thing here. This should have been a. All right, so this is not affecting anything. So 0 is the identity element for addition. Is there a comparable number that has the same impact on multiplication? Now, there a number which, when multiplied by a, will give me back a. The answer is yes, but this time the number is 1. So if I multiply any number by 1, I get I'm not changing its value. So we call 1 the identity element for multiplication. Now, sometimes, as we saw earlier, when we were rationalizing those fractions, we put that to good use by rewriting 1 in a more convenient format, but that's all we were doing. So this is how we justify doing that. In other words, let's say you had radical 2 and you multiply it by radical 2/2 or something, or sorry, 2/2 or something like that. The fact that you can multiply by 1 without changing it is coming from this property. So just a quick summary here. Zero is the identity element for addition. 1 is the identity element for multiplication. Okay, I'll just a quick summary. Now, another property which is closely related to what we just did is the so-called inverse property. Now, we often use the word inverse, but it turns out that there are two different kinds of inverses, so we have to be careful. Everybody knows, I guess, that if you take any real number a and add negative a to that, we'll end up with 0. And remember, 0 is the identity element for addition, as we just saw. So because of that, we call negative a the additive inverse of a. because their sum is the identity element 0. So I guess, we don't really need a lot of examples. Let me throw a couple of them in there. For example, let's say that we have 3 plus -3 equals 0. So therefore, -3 is the additive inverse of 3. And of course, any numbers I pick, it'll be the same thing. -4 is the additive inverse of +4. So it's a pretty straightforward idea. Now, what about multiplication? When you use the word inverse, this is the one that you're probably thinking of. If I multiply a times 1 over a, of course I'll end up with 1. And so therefore, we're going to call 1 over a the multiplicative inverse of a. Okay, so just as a quick example, and I'm sure this will be very straightforward. I'll just leave it like this. 3 times 1 over 3 equals 1. Therefore, 1/3 is the multiplicative inverse of 3. Okay, that's true for negatives as well. So therefore, 1 over -2 is the multiplicative inverse of 2. So, often in math, you hear people say the word inverse. Usually when they say inverse without specifically specifying which one they mean, they're usually talking about the multiplicative inverse. But just be aware that there also is an additive inverse. All right, now finally, here's another one that you have definitely been introduced to. It should bring back a lot of pleasant memories. That would be the distributive property. How does that work? Oh, yes. You've done this all of your life, basically, maybe without remembering the name of the property. If I have A multiplied by B plus C, what I'm supposed to do, or I can do, is multiply these two to get this one, and then multiply A by C, whoops, to get to this one, okay? So we call it the distributive property of multiplication over addition because you're multiplying and then adding. Okay, so let me show you some actual numerical examples. When you see these again, you'll say, oh my God, this is so easy. Here, for example, now remember, because we're mixing different operations, we always do the parentheses first. 2 times parentheses 3 plus 4 is 2 times 7, which is 14. But if I apply the distributive property, I've got 2 times 3 and 2 plus 2 times 4, which means 6 plus 8 or 14. So this is a demonstration that this actually is working correctly. Then we do the same thing here. We should evaluate this first to come up with -30, or use the distributive property. -3 times 4 is first, and then to that I add -3 times 6. That gives me -12 minus 18, and of course, it's the same thing. Excellent. And of course, yes, you can admit it now. You remember this, don't you? Yes, you do. All right, now we're going to switch our gears a little bit here. And we're going to revisit something that you should already be familiar with, but possibly need a little more review. The idea of exponents, and we're going to follow that up with something you've seen in science classes, scientific notation. Now, you might recall that scientific notation is designed to let us represent either extremely large or extremely small numbers. It's often very helpful, like for example, in chemistry class, you might recall you had some very large numbers, like the number of molecules in an, let's say in an atom, or the number of atoms in a molecule, I should have said, or maybe Avogadro's number, or the speed of light in physics class. Those are gigantic numbers, but you also have tiny numbers, like the the weight of an electron is really, really tiny, and it needs to be expressed with scientific notation. But just as a formal definition, what does an exponent even mean? A to the nth power means you're taking a and multiplying it by itself n times. Okay, that's what it actually means. It's a shorthand way of saying I'm going to multiply this number by itself a given number of times, which in this case is n. Now, there's formal terminology here, of course, that, like you would expect, for a to the n power, we say that a is the base and n is the exponent. Okay, base, exponent. I'm sure you all remember that this is an exponent. You might not have remembered that this number that's being raised to n is called the base. Okay. Let's look at a few quick examples. So 2 cubed is 2 times 2 times 2, which is 8. 3 to the 4th power is just 3 times itself 4 times, which turns out to be 81. And finally, 5 squared is just 5 times 5, which is 25. Okay, so it's very straightforward. But you'll notice in all of these cases, we have a positive integer. It doesn't always work out that way. We have to know what to do when we have exponents that are not positive exponents. All right, the rules might surprise you. All right, so I'll call these special cases. So just as a quick example, what happens if we use an exponent of 0? Okay, what do you do with that? I mean, how do we interpret that? Well, for any real number a, if I raise it to the 0 power, I'll just get 1. Okay, so you might remember that one. If you're not sure, you can always double check these on your calculators. All right, now how about 1? What happens when the exponent is 1? That's an interesting case because you just end up with the number itself. So 3 to the 1st, for example, is simply 3. And in fact, whenever you write an exponent, a number, any kind of variable or a constant, x implicitly can be written as, there's a 1 here. In other words, there's an implied 1. When I write x like this, all the other exponents, I have to write them. For example, x squared. But here, I can get away with leaving it out because it's understood that without an exponent, it's assumed to be a 1. Or what about 3 to the 1st power? That's just 3. Whereas 3 squared, I have to write it like that. Okay, so here, the 1 is not absolutely necessary. It's understood that the exponent is 1. Now, here's something that causes people a lot of trouble. Negative exponents are not what you might think. Okay, a negative exponent means we're taking a multiplicative inverse. So for example, 3 to the minus 2 is 1 over 3 squared, which is 1 over 9. So the negative means don't make it negative, take the inverse. Okay, so 3 to the minus 2 is the same as 1 over 3 squared, which in turn is negative, positive 1/9. It is not a negative number. I find that this is the one type of exponent that gives people the most trouble. That's why I'm harping on it a little bit here. All right, how about these two examples then? Well, I've already unfortunately used up one of them, but so 5 to the minus third power would be 1 over 5 cubed, which is 1 over 125. And if you want to calculate the decimal value of that, that's fine. All right, now, you know what we haven't addressed yet? What about fractional exponents? That actually, we have discussed this already because this is what led to our discussion about radicals and roots. Okay, but let's just quickly run through them again. For example, a to the 1/2 power is another way of expressing the square root of a. And of course, if you want, you can write that as 0.5. Now, how about this one? Oh, a to the 1/3 power. This is the cube root of a. If you write it with the root notation, you'll get a 3 in there. You have to put a 3 here. Here, there's an implied 2. We don't usually write it, but there is an implied 2. I think your calculator actually does show the 2 on your keyboard. I'm going to go double check that real fast. But that's kind of unusual. Most of the time, that's not how it's done. We just leave it with blank there. And yes, I wasn't misremembering things. On your calculator, it does actually have the 2 there on the square root button, but it's not absolutely necessary. It's understood that if that 2 is missing, it is a square root. Okay. What about this one, though? This is an odd case. 2/3. What is that supposed to mean? Well, here's what you have to think about. A to the 2/3 power is the same thing as a squared all raised to the 1/3 power. That's the key to the whole thing. Because now you can see that I'm being told to take the cube root of a squared. Now, if you wanted to do this on your calculator, you would have to, let's say you were told to take 64 to the 2/3 power. You would put 64 exponent, open parentheses, 2 divided by 3, close, equals. I think that'll do it. Hold on one second. Making sure 64 exponent, which is x to the y power, open parentheses, 2 divided by 3, close parentheses, and that will give you 16. And here's a hint. If you get it backwards, you'll get a number that's larger than the original value. Like if you accidentally did a to the 3/2, you get more than 64, and you know that that can't be right. A fractional exponent guarantees that your result will be less than a. So let's look at a few of these. So obviously the first one we can tell. It's square root of 9 is 3. If you plug this into your calculator, 8 to the 2/3 power is 4, because what you're actually doing is taking the cube root of 8 squared, which is 64, and we just got through seeing a second ago that that's equal to 4. And then the cube root of 8 is simply 2. And you should be able to do all of these on your calculator. Now, the calculator does have a cube root button and a square root button. Anything else, you'll have to use the x to the y key. All right. Now, we do have some rules for algebraic operations on exponents, which we will save for next time because it's fairly complicated. And when that's done, we can then pick up with scientific notation. In the meantime, though, what I'd like you to do is start working on that first problem set. This one, number 1, not for Thursday, but for next Monday. Okay, it's a little, well, it looks longer than it is because these are not very difficult questions. So we'll do this on a regular basis. As we learn new material, we'll work on these problem sets so that in effect, you're already studying for the first midterm when you do these. And then before the actual midterm, we will have a very long practice problem set, which is meant to cover everything we did up to that point. So you'll be really and truly ready for the midterm. Okay. So in the meantime, I guess we'll have to stop right now. Like I said, I don't want to start this and then have to pick it up again next time, just because it gets a little intense. So we'll leave it off here. And then if you have any questions, you can let me know. Otherwise, I will see you all on Thursday. Okay. That's weird.
I have a quick question.
Oh, go ahead.
So on the syllabus, it says that we have 2 midterms and a final, right? So
Yes.
those are only grades for the whole entire semester?
Yes.
There's no homework or?
No.
Oh, wow. Okay. So do you have the dates planned out for that, or is that going to be? find
No,
out
no,
later?
we have to play that by ear.
Okay. Oh, yeah. Awesome. Thank you.
Okay. All right. You're welcome.
Take
Okay,
care.
bye.